Assalamu alaikum, dear student. This is lecture number 2 of week number 7, and we are continuing the chapter number 7, dimension analysis. The learning objective of this chapter we have already discussed in the previous lecture, and now we are going to continue the remaining part of the dimension analysis. So let's see what are the topics we are going to cover today. So the topics we are going to cover today are the Buckingham-Pi theorem. Okay, this is a method or technique to find out the dimensionless numbers or find out the dimensionless groups, and then we will see the procedure that how do we find the dimensionless groups or numbers, and finally we will do some practice problem of this topic. So let's start. What is the Buckingham-Pi theorem and how do we determine the dimensionless group? So Buckingham-Pi theorem, a fundamental question related to this theorem is how many dimensionless groups are required to replace the original list of variables. So in the previous lecture we finally conclude that in this technique basically what we do, we reduce the number of variables, okay, in a phenomena or in the analysis, because if you have more number of variables then you have to perform so many experiments and it is very difficult to relate with them with each other. Okay, so by this technique what we can do, we can reduce the number of variables. So how many variables we can reduce, this is a question in this topic, and how we can reduce and how many numbers of variables we can reduce. Okay, so the answer is, if an equation involves k number of variables, okay, if an equation or if your phenomena or if a problem is involved with k number of variables, it can be reduced to k minus r dimensionless groups. Okay, so the dimensionless group you will be needed, that will be equal to k minus r. So where k is the total number of variables in a problem and where r is the minimum number of reference dimensions required to describe the variables, because each variables can be defined with the help of fundamental or basic dimensions. Okay, because each variable is made of basic dimensions. So how many dimensions are involved in all those variables involved in a problem, that we have to see. So r is basically representing the total number of dimensionless numbers or dimensionless quantities in the total number of variable in a problem. Okay, so what are the reference dimensions? We all know we have a two kind of system, that is FLT system or MLT system. Okay, in FLT system, so total number of fundamental dimensions we have 7, but the problem we are discussing in that problem maybe 2, maybe 3, maybe 4, maybe 5. But normally the cases we deal with, normally we come across with maximum 3 basic dimensions, which is MLT or FLT, and sometimes 2. Okay, rarely we find a problem where we come across with 4 dimensions or 5 dimensions. Okay, so mainly the case we handle in which the basic dimensions involved in all the variables are 3. Okay, it could be either MLT or FLT. Okay, so the dimensionless group obtained from the Buckingham-Pi theorem are called pi terms and denoted by symbol pi. Okay, so the group we formed, okay, the group we formed by using the Buckingham-Pi theorem is called pi term, and we represent those groups with symbol pi. So pi is the dimensionless number which has no unit. Okay, so pi representing the dimensionless number. Okay, and each dimensionless number is called pi terms. So let's see how we determine the pi term and how do we form the dimensionless group. So we will go step by step and we will see. So there are several methods available to determine the dimensionless group or pi term. Okay, so for example, we have two basic techniques, that is basically the Rayleigh method and the Buckingham pi theorem. So Rayleigh method had its own limitation. It cannot handle more than 2-3 variables. Okay, if a system has more than 3 variables, so the Rayleigh method is very complicated to resolve. Though we have a solution, but it becomes very complicated. Okay, so up to 2 variable and 3 variable it handles very well, but if a case or problem have more than 3 variables, so it is very difficult to handle by using Rayleigh method. But in the Buckingham pi theorem, doesn't matter how many variables are involved in a system, the solution and the method is very simple. Okay, so the method we will study here is called the method of repeated variables. So Buckingham pi theorem is also known as the repeated variable method. Okay, so now let's see the step-by-step procedure to follow the solution, that how do we find the dimensionless groups by using the repeated variable methods. And what is the repeated variable method, we will explain in the further steps. So let's see the first step, what we do in the case to determine a dimensionless group. So first step is list all the variables that are involved in the problem. Okay, so whatever is the problem you are going to experiment or you are going to analyze, so list out all the dependent and independent variables. Okay, so first step you have already now to minimize. Okay, now there are some useful guideline to reduce the number of variables, because more you have number of variables, it will be more difficult to analyze. Less you have number of variables, but it doesn't mean that you leave some important variables. So all the necessary variables at which the variable that you want to conclude the result, so you have to see the basic result you want to achieve. So what are the variables are affecting those results? For example, if you want to find out the drag force in the air, on the water, so you have to consider all the variables which are affecting the drag force. So if you want to find out the pressure drop in a pipe, okay, so you have to consider all the basic factor which may affect the pressure drop in a pipe. Okay, so in that case the pressure drop would be dependent variable, and all the variables that will help to find out the drag force or that may affect the drag force is called the independent variable. Okay, and all the pressure drop in a pipe is a dependent variable, and all the variables which may affect the pressure drop, such as diameter, such as length, such as density of water, viscosity of water or viscosity of fluid, density of fluid, velocity of fluid, these variables are independent variables, because the pressure drop in a pipe will depend on those variables. Okay, so now we are going to give you some tip to reduce the number of variables in a problem. So to minimize the laboratory work, we want to keep minimum number of variables. Okay, so therefore it is important that all variables be independent. Okay, for example, if cross section area is an important variable, then either area or diameter is used, not both of them. Okay, so you can see if you have a circular pipe, so you can see, So you have two parameters, dia and area. If you know the diameter, you can calculate the area, or if you know the area, you can calculate the diameter. So in both the cases, the basic parameter is diameter. The basic variable is diameter. So you don't have to consider both the variables, area or diameter. If you consider one of them, because the area is depending on diameter, diameter is not depending on area. Okay, so if you know the diameter, if you consider the diameter, automatically you can calculate the area. So so in that case, we can avoid considering area as a variable. So in that case, we will take only one variable, that is diameter, and that will fulfill the requirement of the area as well. Okay, so in a same way, the fluid properties, the density and the specific weight, because the density and specific weight almost belongs to the same family. Because you see, if you know the density, you can calculate the specific weight. If you know the specific weight, you can calculate the density. So if you are considering density as a variable, so you don't have to consider another variable which is specific weight. So you can avoid an additional variable, that is specific weight, because this is depending variable and this is an independent variable. So here density, we are considering a variable, and we are reducing one more variable as a specific weight. Okay, so now the step 2. So this is the idea to reduce the number of independent variables. Okay, so similarly, the step 2, express each of the variable in terms of basic dimensions, either MLT and FLT. So whatever the variables you have, we know that all the variables are made of basic dimensions. So write all the variables either in the form of MLT or in the form of FLT system. Suppose we have a velocity is equals to meter per second. So meter is, you can change with L, and second you can change with T. So what is the basic dimension of velocity is L over T, or L T minus 1. In the same way, you can write down the viscosity, you can write down the density. So density meter cube, the mass per unit volume. Okay, so mass over volume. So what is the unit of mass and what is the dimension of mass? That is m. If it is MLT system, straight away you can write down m. And at the denominator, you have a volume, that is L cube. V is basically volume, that is L cube. So m over L cube, or m into L minus 3 is the basic dimension of the variable density. Okay, so in that case, express all the variables of the problem in terms of MLT or FLT system. So now in the step 3, determine the required number of pi terms, or determine the required number of dimensionless numbers, that how many dimensionless numbers you can make in that problem. Okay, so basically pi term indicates the number of dimensionless group. Okay, so how you can achieve? You can achieve by k minus r. What is k minus r? K is the total number of variables. Okay, variables including dependent and independent. Okay, it doesn't mean that you are considering only the independent variables. Don't consider dependent and independent variable both. So k is the total number of variables in a problem, including dependent and independent variables, where r is the total number of basic dimensions involved in all those variables. Okay, what are the basic dimensions? You can see all the variables are made of a basic dimensions, m, l, t, theta, I, because there are seven number of basic dimensions, but in most of the variables only 3 basic dimensions are involved. Either it is MLT or FLT, that we already have discussed in detail. Okay, so so you just count it that how many dimensions, how many basic dimensions are involved in all those variables. Okay, so count them, and that basically indicates the R. So k minus R will give you the total number of pi terms you needed or you required. Okay, so what is the step number 4? Step number 4 is selecting the repeating variable. So this method is called the repeating variable method or the Buckingham Pi theorem. Okay, so what is a repeating variable? Repeating variables, you can see here, the number of required repeating variables is equal to the total number of reference dimensions. Okay, if you have a reference dimensions 3, so the total number of repeating variable will be 3. If you have a total number of dimensions 2, the total number of repeating variable will be 2. Okay, so if you have a total number of basic dimensions or fundamental groups or fundamental dimensions are 4, so your repeating variables will be 4. Okay, so this is the first step. Though how many repeating variables you have to use, so it all depends upon the basic dimensions involved in all the variables in a problem. Okay, so now second, select the repeating variable in such a way that all of the reference dimension must be included within the repeated variable. Okay, so select the repeating variable in such a way that all of the reference dimensions must be included within the repeated variable. Okay, so what does it mean? It means that the repeating variable must have all the basic dimensions. Okay, so you should not select a repeating variable, those variable in which all the dimensions are not being used. Okay, so that I will explain to you also. For example, what does it mean? That means it is better I will explain when we will do the problem. Okay, here it is a bit difficult to explain here. Okay, but it is very obvious. I will this is, you can understand also by reading this. Okay, select the repeating variable in such a way that all of the reference dimension must be included in the repeated variable. The variable you are selecting as a repeated variables, all the dimension, for example, if it is MLT system, so all MLT must be there in the repeated variable. Okay, if any one of them, suppose the repeated variable you have selected, and if M is not there, okay, though M is present in the other variable, so that means the variable you have selected as a repeated variable is wrong, is not correct. That will give you a problem in other cases, in somewhere in the solution. Okay, so this is what it's mean. Okay, so now the third guideline, each repeating variable must be dimensionally independent. Each repeating variable must be dimensionally independent to the other repeating variables. Means the dimension of one repeating variable cannot be reproduced by the combination of product of power of the remaining repeating variable. Okay, so what it's mean? It's mean the dimension of the repeating variable. Okay, once again we can read out, each repeating variable must be dimensionally independent, okay, to the other repeating variables. Okay, means the dimension of one repeating variable cannot be reproduced by the combination of product of power of the remaining repeating variables. For example, if you have 3 repeating variables, just like just like diameter, density or velocity, so velocity has its own dimension. Okay, so if the dimension of velocity can be reproduced by the combination or by the combination of the density and the velocity, density and the diameter. That means this is not the right selection of the repeating variable. So the repeating variable is such, the dimension of that repeating variable cannot be reproduced with the combination of the remaining uh, remaining repeating variables. Okay, so this is the point, another point. So do not select the dependent variable as one of the repeated variable, otherwise it will appear in more than one group. Though it is not wrong, but it will create complication in the calculation. So it is better not to select the dependent variable as a repeating variable. Okay, what will otherwise what will happen, it will appear in more than one group, and if you, when you have to find out the dependent variable or the value of dependent variable, it would be difficult for you to separate from each other. So it is better to not select dependent variable as a repeating variable. So that gonna be helpful, that gonna be helpful for you when you determine the value of the dependent variable. Okay, so step number 5, form a pi term. So now form a pi, how can we form a pi term? So pi term we can form by multiplying one of the non-repeating variable. Suppose if you have total number of 5 variables, and out of 5, 3 variables are repeating variable and 2 of them are non-repeating variable. So that means non-repeating variables are 2 and repeating variables are 3. So by multiplying one of the non-repeating variable, so out of 2 take 1 and multiply with the variable with the product of repeating variable, multiply with the product of repeating variable. So that means 3 repeating variable multiplying with the 4th non-repeating variable, and each raised an exponent that will make the combination dimensionless. So each repeating variable would have an exponent, okay, with unknown, that would be unknown exponent. So each repeating variable would have an exponent, okay, and those exponent variables will multiply with the non-repeating variable, and in that way it will form a dimensionless group. Okay, so another point, determine the value of exponent such that the resulting exponent must be 0. Okay, so now the objective is to determine the value of exponents. Okay, so here step number 6, repeat step number 5 for the other non-repeating variables, and again then after developing the dimensionless group, we have to cross check the dimensionless group we have formed, it is really a dimensionless group or not, it is basically fulfilling the requirement of the dimensional homogeneity requirement or not. So we cross check and verify, and after that we express the final form as a relationship among the pi terms. So how we represent the pi terms, because here we write down the pi term involved with the dependent variable, and the is a function of pi terms involved with the independent variables. Okay, so that's why where pi 1 would contain the dependent variable. So dependent variable is a function of the number of pi terms involved with independent variables. Okay, so let's see how we can apply all those steps in a practical problem. So here there is a problem is given. So here is the example. So at a sudden contraction in a pipe, the diameter changes from D1 to D2. The pressure drop del P which develops across the contraction is a function of D1 and D2, as well as the velocity V in the larger pipe, and the fluid density rho and viscosity mu. Use D1, V and mu as a repeating variable. So please note down, use D1, V and mu as a repeating variable. variables to determine a suitable set of dimensionless parameters. Okay, so why would it be incorrect to include the velocity in the smaller pipe as an additional variable? So first we will try to understand the question, and then we will go to find out the dimensionless parameter step by step as we have studied just now. Okay, so first of all, in the question there is a contraction in a normal term we say is a reducer. Okay, so we understand before and after the reducer there is a straight pipe. Okay, so before the reducer, in the upstream side of the reducer the diameter is larger. Okay, so and the downstream side the diameter is smaller. This is in the case of contraction, and there is another, that is expander also. That is also a case of the reducer, but that is expander. In the what is the difference? In the expander we have a upstream side the diameter is smaller, and the downstream side is the diameter is larger. But here we have a contraction, the reducer. In that case the d1 is greater than d2. Okay, so we have to find out, definitely we are changing the size of the pipe. So in the case of real fluid definitely there is a pressure drop. Okay, because of the geometry. Okay, there is a pressure drop. So what is the amount of pressure drop when you change the diameter from d1 to d2? And d1 and d2 can be any diameter, right? So these are the variables. Okay, so we have to develop the pressure drop. So pressure drop is basically a dependent variable, and this pressure drop is depending on several variables. What are those variables at which this pressure drop is depending on? That is d1 diameter at upstream of the contraction, and d2 diameter at the downstream of the contraction. And what else are the variables? That is velocity of the fluid which is passing through, and the density of the fluid, and the viscosity of the fluid. Okay, so here are the 5 variables which are depending, the 5 variables at which the pressure drop in a contraction is depending. So and here you see there is another part of this question. They use d1, v and mu as a repeating variable. So this technique to form a dimensionless group is called a repeating variable technique also. So in this case the repeating variables are given. Okay, so keep in mind here the repeating variables are given in the problem, but in some cases, in many cases or in many problems, the repeating variables are not given. So you have to choose the repeating variables by yourself. So how would you choose the repeating variable? So I am going to explain here at the moment, so please note it down properly. So here you see, so whenever you have a problem and in that problem you have many variables, so what are the variables supposed to be repeating variables, and what are the variables are supposed to be non-repeating variables? Suppose the repeating variables should have 3 different properties. The first repeating variables from the variables which has a geometrical properties such as volume, area, length, width, diameter. So these properties are called geometrical properties. So you can select one of the variables from the geometrical properties. Suppose if you have many variables, if you have a variables in which you have an area, you have a diameter, so you can select one of the variable as a repeating variable. So here we have, you see, diameter d1 and d2, and both of them are independent variable, because the upstream dimension and downstream dimension has no relationship. Okay, so if you have a diameter upstream at d1, so you cannot say if you know d1 you can calculate d2. You cannot, because our downstream diameter can be any diameter. So d1 and d2 are independent variable. So you can choose one of the repeating variable from d1 and d2. So here in the problem they have given to you to take d1 as a repeating variable. So if it is not given in the problem, so you may take d2 as a repeating variable as well. You can take d1 and d2. Out of 2 you can take anyone. So the first variable you can choose from the geometrical properties. Okay. The second repeating variable you can choose from the flow properties. Okay, flow properties of the fluid, just like the velocity, just the volume flow rate, the mass flow rate, the acceleration. So these are the properties are called flow properties. Okay, so that means here we have the problem we have, in which we have one variable only which has a characteristics of a flow properties, that is velocity. So we choose velocity as a second repeating variable. Okay, so now the third repeating variable from the fluid properties such as the surface tension, the viscosity, the density, the specific weight, the specific gravity. So these are basically the fluid properties. So fluid properties, you have a two fluid properties, the density and viscosity. So you can, if since in the problem viscosity is given to consider as a repeating variable, suppose if it is not given in the problem, so you may choose, you have a choice to choose mu or rho as a repeating variable. Out of the two you can choose anyone. Okay, you are free to choose rho or free to choose mu if it is not given in the problem, right? So the first repeating variable from the geometrical properties, second from the flow properties, third from the fluid properties. Okay, so these are the criteria to select the repeating variables if it is not given in the problem. And now the last part of the problem, why would it be incorrect to include the velocity in the smaller pipe as a additional variable? So we have to also verify that why we did not consider the velocity in the downstream condition, okay, as an independent variable. So that we have to also prove that. So let's see how we develop the dimensionless group. So what is the first step? List all the variables that are involved in the problem. So what are the variables involved in the problem? We have listed out here. So here you see the pressure drop is depending on the following 5 variables. So what are the total number of variables? 5 or 6? The total number of variables are 6. Okay, so here k is equals to 6. So regardless the variable is dependent or independent, the total number of variables including dependent and independent is 6. So k is equals to 6. So what is the next step? Next step is to express each of the variables, dependent or independent, in terms of the basic dimension or the fundamental dimensions. So we know the unit of all the variables, and so we are going to replace with the abbreviation of the basic dimensions. Okay, so we replace all the variables with the basic dimensions. Okay, so the pressure drop is force per unit area. So we are going to deal with the FLT system here. Okay, so we are going to deal with FLT system. So here we replace force with F and area with L square. Okay, so here diameter is basically the dimension L, diameter 2 is the dimension L, and velocity is meter per second. So meter is length and second is t. Okay, so same is the density. We converted mass into in terms of force. Okay, so how did we convert it? Because force is equals to ma and m is equals to f over a. So we converted m is equals to f over acceleration. Acceleration is L over t square. So it come up, so it become density. So here the viscosity also we converted in terms of force. Okay, so now the third step, determine the required number of pi terms. So what is the required number of pi terms? K minus r. What is k? K is the total number of variable, and r is the what? R is the number of dimensionless, basic number of dimensions in the total number of variables. So what are the total number of variables in the in the total variables? You can see, we can see here F, L, 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 T, F, L, T, F, L, T. So we are seeing only 3 dimensions. Here F, here L, and here T. And these dimensions are repeating. Okay, so that means we have R is equals to 3. So the total number of dimensions in all used to form all the variables are 3. So R is equals to 3. So here you can see the number of pi terms or the number of dimensionless group we can form, that is 6 minus 3, the total number of variables minus total number of basic dimension used in the variables. So that is equals to 3. So 3 is the dimensionless parameters required. So the total number of dimension groups or dimensionless parameters that we can form is 3 in this problem. Okay, so how we can form? So select a repeating variables. So since the repeating variable is already given in the problem, so if it is not given, so we can select the way I explained to you and the guideline I provided you to select the repeating variables. So the repeating variables are D1, V and mu as a repeating variables. Okay. So step number 5. In this step number 5, what exactly we do? We are going to form the dimensionless group. And how do we form the dimensional group? It is completely explained in step number 5. So by using this, what we have to do? We have to consider one non-repeating variable and 3 repeating variables. Repeating variables with the exponent power, okay, and non-repeating variable with no exponents. Okay, so they are going to be multiplied with each other. So the first dimensionless group is pi 1, that is equals to, so we are considering the delta p as a non-repeating variable here with the repeating variable in the first pi term, okay, or first dimensionless group. So here the repeating variable with the exponents power. Okay, so what we are going to now, we are going to replace all the variables with the basic dimensions. Okay, so what are the basic dimensions? These are the basic dimensions given. So we are going to replace delta p with this, d is with this, v is with this. So let's see. So we replace all the variables with the basic dimensions, and these basic dimensions are equal to the dimensionless number. This is a dimensionless number. So basically pi 1 is a dimensionless number or dimensionless group. Okay, so it's a dimensionless number or dimensionless group. So you see f naught, l naught, t naught is a constant. It has no dimension. Okay, so that's why this term is equal to this term, and we replace this all is a dimension. So now we are going to equate the power of each dimensions. So here we are going to, I repeated the previous steps here. Now we are going to compare the force both sides, the exponent power of both sides. Okay, so here f is equals to 0. We are comparing f now. So f ki power 0, the power of f is 0, and here you can see f. Here f is equal, f has exponent 1. So here 1 plus you can see f is exponent c. Okay, so this 1 plus c equals to 0. So now again we are going to compare L. So L is equals to 0 on the right hand side. Now the left hand side, L is equals to minus 2. So it's going to be minus 2. So here L is plus A. So L is plus A. Here L is plus B. So L is plus B. Here L is minus, and this is 2C. So minus 2C. So L is here minus 2C. So now third equation we will make based on the time. So that is basically t is equals to 0 on the right hand side, and the left hand side, where is the time? It is not here, not here, not here, t is here. So this is minus 1. It is going to be multiplied with b. So it's going to be minus b. So it is here minus b. So it is here t is the power 1 multiplied with c is going to be c. So plus c equals to 0. So now we have to find out the value of a, b, c. So when we simplified these three equations, 3 unknown, so we end up with the value of a, b and c equal to like this. So now we are going to put these values in the very first equation, that is here. We are going to put the value of a, b, c in this equation. So what will happen when we put this value a, b, c here? So let's see, after replacing the value, so is going to be pi 1 will become like this. Okay, because b and c has a minus value, so those two variables will come in the denominator. Okay, so this is pi 1. In the same way, now we can find pi 2 and pi 3. So we're going to repeat step number 5. for pi 2 and pi 3. Okay, so before that we also have to verify whether the dimensionless group we have formed, it is right or wrong. Okay, it is dimensionally homogeneous or not. So what we have to do, we have to replace all those variables with their basic dimension. So we put all the basic dimensions, okay, in MLT group. Okay, to check the dimensionless parameter, we are considering MLT system, the cross check, okay, whether this group is valid for both the system or not. So we put the value in the MLT system, and finally when we balance all the variable, it become M0, N0, T0, and this is a dimensionless number. That means the group we have formed, the first group we have formed, or the first pi group, is a valid dimensionless number. Okay, so in the same way we form the group pi 2, and pi 2 we calculated d2 over d1. Here we got a is equals to -1, b is equals to 0, c is equals to 0. When we put the value, so this will become 1, this will become 1, and here is equals to minus d1. So it becomes d2 over d1. So definitely it is a dimensionless group, because this is also L, this is L, so there is no need to cross check. So L and L will gonna be cancelled, and it's become a constant and a dimensionless number. Okay, so now same way we calculated the dimensionless 3. To create the second dimensionless group, we consider all 3 repeated variables with the exponent, and consider another non-repeating variable. So d2 is another non-repeating variable. For the third group, we consider 3 repeating variable with the exponent, and consider another non-repeating variables. Okay, because out of the 6 variables, 3 were repeating and 3 were non-repeating. So non-repeating variables come with each pi terms. Okay, so this was the third repeating variable. So finally when we calculated the value of a1, b1 and c1, if we put the value of a1, b1, a, b and c in the exponent here, and finally we end up with pi 3 is equals to rho d1 v over mu. Now we can cross check. So when we cross check by using the MLT system, we end up with M0, L0 and T0. That means this is also a valid dimensionless number. So the dimensionless number can also how can we represent? So this is the way to represent the dimensionless number, because we have to determine the delta p, that is basically the dependent variable. Dependent variable is a function of other 2 dimensionless group, that is this part and this one that we have calculated. Now the second part of the problem, to verify whether the velocity in the downstream condition is a valid variables to consider in the analysis or not. So using a continuity equation, so we know that v1 a1 is equals to v2 a2. Okay, so because v1 a1 is basically the diameters. Okay, so pi and pi is going to be pi by 4 are going to be cancelled. So here v d1 square, okay, and vs, okay, or v2 you can consider. So v and v2, so going to be d2 square. So since you can see, because v2 is depending on the velocity at upstream condition, okay, because since d1 and d2 are independent, okay, but the diameter is fixed, okay, but whatever is the variable is here, it is this variable is depending on this variable. Okay, so if going to be large, so this is going to be accordingly it will increase. So this variable is not independent. Okay, so this variable is dependent on this variable, so we cannot consider the velocity at downstream condition as an independent variable, and we cannot take this variable in the experimental part. So rest of the topics we will cover in the next lecture. Assalamu alaikum.